Okay, welcome back to section 5.6. I'm actually going to skip example 3. You're welcome to do it on your own and look at the Desmos graph, but I think I'm going to go ahead and skip ahead to, I think there was more examples than I needed. I'm going to go ahead and skip ahead to example 4. So let's look at this guy. This has a little bit harder quadratic stuff in it. So what is the domain? Again, we're going to look at the denominator, set it equal to 0, and exclude those values. So there's a couple different ways we could solve this. We could use the quadratic formula or we could use factoring. I've done the quadratic formula a number of times. I think I'm going to try and factor this one. So just because I think it's faster. What are two numbers that multiply to -4 and add to -3? Well, to me, that would be -4 and +1. Double check. X squared plus x minus 4x is minus 3x minus 4. So I have x equals 4 as one solution and x equal to -1 as another solution. So what is the domain? The domain is all numbers except all real numbers except -1 and 4. So to write that in interval notation, we would go from -infinity to -1, from -1 to 4, and from 4 to infinity. That's how we exclude those two values. All right, so what are the vertical intercepts? Well, the vertical line's x equal to 4 and x equal to -1. What are the horizontal intercepts? Now remember, that's where we solve x squared plus 1 equals 0. All right, that's where the numerator equals 0. Let's solve this. We can use the square root method. X squared equals -1. I'm already getting concerned. Take the square root of each side, and we get x equals plus or minus I, the imaginary number, equal to the square root of -1. Yeah, so what does that mean? Well, it means that if we try to set the numerator equal to 0 to find the horizontal intercepts, there's only imaginary numbers. So what that means is there are no horizontal intercepts. Right? You can't graph plus or minus I on the real axis, so there's going to be no horizontal intercepts. There's no time where that numerator equals 0. All right, how do we find the vertical intercepts? Well, we're going to take k evaluated at 0. So that's 0 squared plus 1 over 0 squared minus 3 times 0 minus 4, which is 1 in the numerator and -4 in the denominator. So x equals 0, y equals -1/4. And that's going to be your vertical intercept. All right, this is a pretty interesting graph. I said to sketch what we know so far, but we don't know too much. But I think what we're going to do now is we're just going to go over to Desmos and look at a graph of this. All right, here we are in Desmos. Let's go ahead and graph our example 4. So k of x equals, in the numerator, make sure you use parentheses to get this to work out just right, x squared plus 1 divided by x squared minus 3x minus 4. And there's the graph of our function. That looks pretty good, actually. All right, so what do we see? Well, we had vertical asymptotes at -1. So here's one of them. Actually, we could just go ahead and graph that guy. X equals -1. Put that in there in blue. That looks nice. And x equals 4 was our other one. Let's go ahead and make that blue too. Why not? The vertical asymptotes are blue. There you can see that it approaches the blue but never crosses it. As we zoom out, we can see there really was no horizontal intercepts. It never crossed the x-axis. And we can see the vertical intercept, and if we click right on it, it's at 0, -0.25, which is exactly, we got 0, -1/4. So there's the graph of that function that we found those different pieces for. Hi, welcome back to section 5.6 and 5.6. And now we're going to talk about some information that comes from using the numerator and the denominator together. So you have to look at both of those guys for these next two pieces of information. So before, we had looked at the denominator to find the domain and the vertical asymptotes. We looked at the numerator to find the horizontal intercepts, and of course we used them both a little bit to look for the vertical intercepts. That's the same for all functions. And now we're going to talk about holes. These are not super common, but they are something you need to know about rational functions. And holes occur, I always think of black holes. Holes occur when a value will make the numerator and the denominator 0. Okay, my computer is not scrolling the way I want it to scroll right now. Yeah. All right, so if we look at this function, and we put in 2 for x, we can see that the numerator is going to be 0 when you do f of 2. So f of 2. That gives me 2 minus 2 times 2 minus 3 over 2 plus 7 times 2 minus 2. Well, 2 minus 2 is 0, and 0 times anything is 0. And again, in the denominator, same. So what you end up getting if you plug 2 in there is you end up getting 0 over 0. This is really sort of bad news in the world of math. 0 over 0 is never a good thing. And in fact, when I teach calculus and I say, hey, if you get 0 over 0, this almost always means you need to do some more work. But what it means in terms of rational functions is you need to just be aware of it. And there's a hole in the function. If you actually look at the Desmos graph, here's a Desmos graph of this function. It doesn't even look like there's a hole there, but you should know something is wrong because if you look at the denominator at x equal to 2, we should have something happening. If you zoom in enough, it will actually show you in Desmos that there's no output value. It says does not exist. If you plug in the value 2, it puts D and E for the output. Does not exist. All right. So that's just something to be aware of, that there can be holes in these rational functions. The other thing that happens, I'm trying to get my scrolling here. I lost my mouse. There it is. Okay. The other thing that we get from both the denominator and the numerator together are called horizontal asymptotes. So horizontal asymptotes tell you about long-term behavior on the graph, and they usually look like a graphed dashed horizontal line. Same idea of vertical asymptotes, except for these are horizontal. And they're always of the form y equals some number, just like horizontal lines are always of that form. All right, so let's look at the rules for horizontal asymptotes, and then we'll practice a few of them. So remember that every rational function is made of a ratio of polynomials. We're going to call our numerator polynomial p of x and our denominator polynomial q of x. And polynomial, if we write it in order of decreasing degree, so this is our leading coefficient with our leading term, in both of these, we want to have the highest power in both of those first. When you look at the ratio of those exponents on the leading terms, that tells you about the horizontal asymptotes. So if the numerator power is bigger than the denominator power, then y equals 0 is going to be a horizontal asymptote. So that's the x-axis. If they have the same power in the numerator as the denominator, the ratio of the leading coefficients is going to be your horizontal asymptote. And if the numerator power is bigger, I'm sorry, I think I said that backwards. Back up. If the power in the numerator is less than the power in the denominator, then y equals 0 is going to be a horizontal asymptote. If the powers are equal, then the ratio of the leading coefficients is going to be a horizontal asymptote. And if the power in the numerator is bigger than the power in the denominator, then there is no horizontal asymptotes. We're going to practice seeing what all three of these look like. Okay, first we're going to look at the equations, and then we're going to look at their graphs. So let's look at this example A. The power of the numerator is 3. Okay, so the numerator power is 3. The power on the denominator is 5. So we are in category power. We're in the category that the numerator power is bigger than the denominator power. So we're in the numerator is greater than the denominator. No, we're in the numerator is less than the denominator. I'm having trouble comparing numbers today. The numerator power is less than the denominator. 3 is less than 5. So that means for this guy, y equals 0 is my horizontal asymptote. Okay. Let's look at B. Okay, so this one, the numerator power is equal to the denominator power. So that means we're in the n equals d group here. And that means that the ratio of the leading coefficients is your horizontal asymptote. So y equals negative 14 over negative 7. Negative 14 over 7. So that's negative 2. Y equals negative 2 is my horizontal asymptote in that example. And finally, if we look at the last one, the power on the numerator is bigger than the power on the denominator. The numerator is bigger than the denominator. So when the numerator is bigger than the denominator, there is no horizontal asymptote for that guy. All right, so I know I said state and behavior, but we're going to do that after we look at the graph. Let's go ahead and look at the graphs right now. Here's our graphs. Oops, I scrolled too far. Panicking. Let's make this smaller so we can see these at the same time. All right, let's see if we can match these guys up. So the first one, we said that the numerator was smaller than the denominator power, so y equals 0 is a horizontal asymptote. So if we look down here, which one of these seems to be approaching the x-axis as we go to negative infinity and positive infinity? And that's going to be the red one, right? This is going to be g of x, right? G of x. And we can see as we go to negative infinity, we're going really close to the x-axis. And as we go to positive infinity, we go really close to the x-axis. But we don't actually cross it. It's just getting really close. So my end behavior for this one would be as x goes to negative infinity, then g of x goes to 0, right? That's what I'm seeing here. And as x goes to positive infinity, g of x goes to 0. That's my end behavior for g of x, right? And that's supposed to be a little arrow. So as x goes to negative infinity, the red's getting really close to 0. And as x getting really big, it's also getting close to 0. All right, so which one do we think is, we have blue and green left. Which one of those has a horizontal asymptote at -2, meaning doesn't, extends to -2 in the long run? Yeah, that's going to be blue. So this guy, what did I call that? F of x. So the blue one is f of x, and we can see that as x goes to negative infinity, f of x is going to -2. And as x goes to infinity, f of x is going to -2. So we can say as x goes to infinity, f of x goes to -2. It's supposed to be a -2. Let me rewrite that. -2. As x goes to positive infinity, f of x goes to -2. So either way, it's going to approach this horizontal asymptote. So that leaves k of x to be the green one, right? K of x has got to be the green one. Well, what's going on there for our end behavior? Well, this looks like it's going down to negative infinity, and this one's going up to positive infinity. So it's not approaching any horizontal asymptote. There is no horizontal asymptote to approach. And we can just read this off the graph, as x goes to -infinity, k of x goes to -infinity. And as x goes to positive infinity, k of x goes to positive infinity. And we don't have rules for this. I'm just looking at the graph and seeing what it is appearing to do. We don't have rules like we do for the for polynomials. All right,